Okay, hello and welcome to today's NAFEMS and Revolution in Simulation webinar on the digital thread in SPDM. Will this bring simulation out of the shadows? My name is Andrew Wood, Regional Manager for NAFEMS in the Americas. With me today are Ernesto Motola, Senior Manager of Model-Based Development at Toyota Motor Europe Technical Center, Jay Ganjuli, Associate Director of Digital Thread Solution Architecture at
Raytheon,
and Malcolm Pentaki, co-founder of Revolution and Simulation.org. Before we begin the webinar, I just want to mention if you have any questions for our presenters during today's webinar, please use the Q&A feature and not the chat feature. Again, use the Q&A feature. All right, and let's get started with a brief introduction to NAFEMS. If you're not familiar with us, we are the International Association for the Engineering, Modeling, Analysis, and Simulation Community. Been in existence for 36 years. And just want to highlight here that in NAFEMS, over 1,400 companies worldwide are members, encompassing industrial practitioners, vendors, and academic institutions. Now, many of you in attendance might have participated in the Simulation 2020 webinar series that we hosted just a few years ago, which was focused on the business, technological, and human enablers driving change over the next 5 years. Now, this series resulted in 14 webinars, covering democratization, simulation governance, and business challenges, being delivered to around 2,200 individuals over the course of a year. You can find many of these webinars by visiting nafems.org or the Revolution and Simulation website. Now, more recently, the Revolution and Simulation and NAFEMS communities have been discussing ideas for a new series, and systems thinking in the technology areas involving simulation became the focus of those efforts. As a result of those efforts, we decided to look beyond the present to the next 10 years of advancements in simulation that are needed to support systems thinking for a model-based enterprise. The series will explore how the latest technology trends and simulation methods will develop and impact our industry and society during the next decade. We'll be exploring the concept of pervasive systems thinking and simulation, which we addressed in the first webinar, a digital thread in SPDM, which we're covering today. And in future sessions, we'll cover other topics like model-based engineering on June the 23rd, generative design, AI, data-driven models, and machine learning, Industry 4.0 and 5.0. More information and registration links for these webinars will be published in the coming weeks and months. Our plan for this series is to lead into Case 20. That's a virtual conference hosted by NAFEMS and Digital Engineering Magazine, taking place next week, June 16th through 18th, online. 2 of the nearly 200 contributions delivered at this event will include content related to this webinar series. You can find more information about this event by visiting nafems.org/case20. And with that, I'd like to turn it over to Malcolm Pentaki, co-founder of Revolution and Simulation.org. And Malcolm, the floor is yours.
Thank you, Andrew. The Revolution in Simulation initiative was launched at the NAFEMS CASE conference in 2018. It's a free web portal that gathers together in one online space all the resources that you might need to take your simulation investments to the next level. It focuses on next generation simulation usage, helping your organization to maximize the impact of simulation on your business goals. Case studies are an important resource that's available on this Revolution and Simulation portal. We've gathered together well over 80 to 90 interesting cases, and the list continues to grow. You can find what your industry peers are doing to increase the impact of simulation in their organizations. Please join the community and contribute to your own success stories. A number of industry leaders and thought leaders have volunteered their expertise, knowledge, and time to be moderators of a growing list of topics of interest. They curate freely available materials and reference them on the different topic pages on the site. You can access these under the How It Works menu. You can ask questions and start discussions with these moderators. Once again, please join us, contribute your thoughts and materials to share with the community. With the help of the moderators and our community, we've gathered together a large trove of resources. You can access these under the Resources tab. Very few of these are actually stored on the site. The site itself provides a short summary of a resource and then points to its original location on the web. If you have resources that you think would be of value to the community, please join us and contribute. And finally, REPSIM has a growing list of sponsors, industry thought leaders that are an integral part of this revolution in simulation. The sponsors provide much more than financial resources to the community and are critical to the ongoing success of this initiative. So join us at repsim.org. It's a valuable resource that's available free of charge. Thank you for joining this webinar. Hope you enjoy the rest of the series as well. And with that, I'd like to hand it over to Jay Ganguly, Associate Director of the Digital Thread Solution Architecture at Raytheon Technologies. Jay?
Thank you, Malcolm. This is part of this series. One of the topics that we have covered in the past is the notion of a system model. So what I'm going to attempt now is trying to understand what is the significance of the system model vis-a-vis a simulation lifecycle manager and how it interacts with simulation. The story so far is that the system model is a core artifact that holds the thread together and plays an important role in connecting silos. That's a grand central station through which the digital thread flows. And the key takeaway from the previous presentation was that while building the system model, a simplistic reductionism in systems decomposition, as is prevalent now, does not work. An approach of breaking things down, building each piece in a silo and assembling them using a set of rules becomes unfeasible. We tend to focus on the trees and ignore the forest until it's too late. High fidelity simulations in silos and low fidelity simulations just don't match as you start assembling things. And the complexity increases exponentially as model gets dynamic, interactions become complex, and it becomes very difficult to assess the impact of change in model or its parameter across various subsystems. So the previous presenter, David Thomas from the Giant Magellan Telescope, articulated a few things in terms of what we have and what we need. And one of those topics was in the need for evolved practices in systems thinking and making the simulation more pervasive and an approach towards assuring data consistency. And there is also a need mentioned for robust access to relevant data design and the capture and reuse of multidisciplinary analysis and enabling of collaboration practices in system simulation. Now, let's explore the interaction between the systems complexity model and the design teams play out in practice. This is an image from a presentation from a DARPA MAKE project. So the RFLP, that is the requirements, functional, logical, physical part of the digital thread, that process that is allocating requirements to subsystems models, it breaks down quickly as the assumptions and objectives used to derive system boundaries change once the function starts interacting. The details of high fidelity interactions happening within the silos is not elevated soon enough in a structured manner until it's too late. The system model-based simulations soon starts losing its relevance with the reality of the complexity that's building up in the silos as you move towards the right side of the V. The complexity in these silos show up in interfaces and model inconsistencies start showing up and simplistic assumptions on subsystem boundaries get invalidated. This is the time to pay up for the lack of rigor in continuously updating the system model with the reality of the domain level complexity as building up. Emergent properties start showing up and it becomes quickly a fragile system, and for emergent properties, there's no explanation in the system model, and we scramble for answers when the cost curve is going exponentially, threatening the program delivery. So A systematic study was done a few years ago by Professor Steve Eppinger of MIT on a system-human dimension of this problem as the system model evolves. The example used was a Pratt and Whitney engine design program. Pratt and Whitney, by the way, as many of you know, is part of Raytheon. So it became part of Raytheon due to the recent merger. So the point is, as the system decomposition is done in this particular engine program, you can see there are 54 different engine components based on various functional cross-design allocated to various functional cross-design teams, which are responsible for each component, and plus an additional set of integration teams responsible for managing the engine level requirements. So what happened was that as the system decomposition is done and cross-functional integration teams formed, there's a cadence of discussion between these teams. What does that cadence look like? So this study refers to two categories of interfaces laid out on a design interface matrix and a team interface matrix. To keep track of the two types of interfaces, one is the unattended interfaces and unidentified interfaces. Unattended interfaces being interfaces defined by the system's architects but lacks a corresponding team interaction. Unidentified interfaces being interfaces the team is working on but does not exist in the system model. So the critical need for the simulation lifecycle manager tool is to enable this kind of an interaction and keep both sides in sync. When it comes to keeping the RFLP part of the system model honest, there is this search for a single source of truth. And this is something that is distributed physically, and even for systems of minor complexity, it's almost impossible to keep it in one physical box. It should be noted that the single source of truth is diluted by the assumptions made during simulation. There is an equivalent distributed systems pattern in software architecture. It's called the enterprise service bus, where the idea of a logical concept of a bus is supposed to hold a single source of truth for all the software systems that are part of the interaction. Again, even in software engineering, that concept of the enterprise service bus is a distributed concept. There's no such thing as a single physical enterprise service bus. It is always distributed. The same thing happens here. The equivalent in our world would be the same thing to the software world would be called a systems model. Systems model is not in one physical location. It is always distributed. So how do we keep track of this distributed architecture in a simulation lifecycle manager and keep it synced with the simulation model? And while we do that, one of the challenges is that these models tend to be very multidisciplinary, and they tend to go around the various hierarchies on how we assemble the models in our product structures and in your simulation bombs. And they are very multidisciplinary in nature, and also the abstraction varies. So if you think of the model complexities in each one of these three dimensions and along each one of these disciplines, the abstractions need to be made consistent between both the systems model and the simulation model. And that is one of the primary capabilities of a simulation lifecycle manager that needs to be kept track of. Otherwise, kept track of before you merge it into the systems model. So that is a key capability. So when you try to juggle these multiple abstractions, another challenge that plays out is the notion of configuration management. How do you do it? How do you do configuration management in such a complex system? And especially when you have software involved in it, where you have the number of interactions just exploding exponentially, right? So that configuration management becomes a challenge. And that level of configuration management capability is simply not there right now in the current state of SLM architecture, because many of them are built on traditional underlying PLM architectures, which are originally meant for CAD data management, and they were purely relational databases, and the concept of scalability, the concept of distribution were not really thought through from bottom up. So the years and decades of IT architecture inefficiencies in the PLM space has caught up, and we are just not possible to manage that kind of complexity in required for SLM, right? So that is that part of the distributed nature of it. Then let's go and spend a few minutes on the distributed data piece of it. As the current challenges is that the most of the infrastructure is on the cloud, and when you want to collaborate using simulations on the cloud and also deal with multiple partners and protect your IP, the capability to share models and share parameters that is reduced to multiple reasons, and also you need to design applications for the cloud. So your traditional client-server based applications, the typical PLM applications and SLM, they don't scale up to cloud. So you have to redesign the SLM and PLM architecture to support this new way of doing things. And the fidelity and rate of simulation data exchange that changes across a collaboration, initiative in a large program. So that is something that has to be the simulation lifecycle manager has to take care of when the digital thread is distributed, geographically distributed, and along with various partners. And to make the problem even worse is this topic of digital twins and physics. So when we say we have a digital twin, where does it exist and how does it participate in the simulation process is the key question. You have time series data coming from the sensors, and you have a notion of a model, and how close is that model, and how is that model influenced by the physics or vice versa, right? So ultimately, you need a model to either be in a central place running, monitoring what's happening to your assets, or also you need one on the edge. The so-called edge model or for the digital thread, what is it that is running and how tightly it's integrated the physics model. And this is a relationship that is kind of outside the realm of SLM architectures right now. And so that is a scale up that needs to happen in the future SLM architectures. So with that set of need for SLM architectures, I am going to present my next presenter, Ernesto Motola. Ernesto is a senior manager for model-based development in Toyota Motor Europe and R&D for vehicle performance. Ernesto, please take on.
Thank you, Jay. Thank you, Jay. Quite some challenge after such inspiring presentation. On my side, I will try to give you some insights on a small yet quite interesting from our side activity we did in Toyota Motor Europe R&D Center to demonstrate the feasibility of realizing in practice some of the ingredients that Jay just described. First of all, I would say that the starting point for this presentation would be the perspective of automotive industry. I'm sorry for all those who are already in the industry if I spend time on explaining a little bit of the challenges we face, all the traditional challenges of a complex product development like a car. I would like to touch upon some of them, like platform commonization, that's a cost-driven requirement, and from a system development perspective has to do with the possibility to reuse the data. On the other hand, we have the need to appeal customers who have different needs, and this drives the product diversification, which from a system lifecycle management perspective has to do again with the importance of variance management. So this is probably what we're used to. They stay always the same and they increase on a yearly basis. On top of this, we have now what our president called a once-in-a-century change, a case, connected, autonomous, shared, and electrified mobility. This is a complete revolution for the automotive industry because it changes completely the needs for the vehicle product. You can see from the latest information shared by Toyota about how possibly the mobility might affect the products we develop. So this means that the requirements would be changing, which means that we have to consider different way for the utilization of these products. At the same time, the services connected to these products make the new need for the systems to interact with other systems, for example, those who provide services. So in general, we have an ever-growing need for a system-centric development. On our side, this is what we are doing already. We have a vision based on model-based development to realize a holistic development of the vehicle and its system through simulation. We aim to continuously develop a virtual environment where the systems and the subsystems can be connected together to realize the performance of the overall system vehicle. This is what we do already. As you can imagine, if you have to imagine how this works in practice, this has to do with a huge amount of data flowing across different disciplines to realize such a virtual environment. However, the reality, from what I hear, not just in our industry, the fact that all these domains have their own legacy, their systems, their processes, and their data sources. So the fact that we have silos has to do with the fact that these are complex data, and the result is that these require effort to extract and reuse in a holistic development approach. So starting from this point, we tackled our proof of concept project on systems lifecycle. We concentrated on the scope to demonstrate the feasibility of improving the process between those who produce the data, like designers, and those who consume the data. So typically what happens in the case somebody has to realize a digital prototype is that the data, typically specification, need to be gathered from a number of sources. So the specification provided typically by designers may be design targets or assumptions, or may come themselves from different data sources like CAD or test results. Too often we see, maybe you recognize the icon, that our processes depend a lot on exchange of data through files. So our first goal was to reduce our dependency on these file exchanges. So this is our intention, to replace a process based on file exchange with a process where the information comes from a single source of truth for engineering specification, in a way that when this is fully developed, everyone can access the same place, and this would reduce the data gathering and review effort. Once we have this in place, as well, this can be used to reuse the data and therefore capitalize past knowledge. Jay was touching about the concept of distributed development. So this data could be used not just by designers, but also by other parties in the value chain, like purchasing, or can use data directly from suppliers. Lastly, what we wanted to demonstrate is once we have data there, whether we could use this to increase the speed and quality of simulation model making process by automation, so that we could enable faster simulation studies with higher data quality. So this is the kind of a scope I will be describing in the next slides. I mentioned a single source of truth, and maybe some of you is asking, really? One more? Well, I think the data model we're intending should complement and integrating with existing PLM solutions. Try to bear with me on a timeline of a typical vehicle project phases. The level of the data detail typically increases. In the beginning, we start with requirement information, which is so well managed today. As the data increase, we go into having a detailed product structure defined with associated CAD data typically. And this has been traditionally well developed, and we have seen many examples of a good connection of this data with typical 3D structural simulation processing with all the related data management. what we think is not as well developed is all the domain of the system performance simulation, which is by definition multi-domain, and the related system specification structure to hold this data, with the requirements to be flexible enough to be suitable for multiple domains, and therefore by definition tool independent to support multi-domain process automation, but at the same time to be connected with the other sources we use during development. So how this system structure look like? So today could be something as simple as a container for the parameters required by the existing simulation models in various domains. So for example, a superset of the parameter for those models. But while we evolve our thinking, this should be flexible enough to support more formal methods, like technical breakdown structures or RFLP or SysML, in a way that basically this data model is really ready to support real systems lifecycle management. Plus, of course, as we mentioned, this should be able to draw, when this information is available, on information available in different data sources. Okay, how to use practically in development. Not all the systems have perfectly aligned development schedule. So the idea is that in certain milestones we'll need to realign. And what typically happens is that from this platform, the simulation engineer would gather the data, build the simulation models, so that the designers can get the results from performance engineering studies, get back into the platform with proposals, get back into design studies for feasibility, maybe with suppliers, reviewing and finally certifying the data for the next phase. This means that basically everyone should be able to have access to the same up-to-date specification across the different domains. Okay, practically, what was our proposed system-centric approach? We worked on the development of a data architecture. In this case, we used the ARS, which provided enough flexibility. We relied on a mixture of built-in data types, like the concept of system. And on top of this, we built some custom data types, which I will explain in a minute. So basically, we have a flexible data structure that we can use from early stage, and what we call engineering data containers, which can handle group or collection of data, which are all the data needed by simulation models. In our POC project, we focused on the mechanical domain, so we had to manage things like parameters, vectors, inertias, curves, or maps. On top of this, of course, we expect from PLM backbone all the typical capabilities like access control, capability to link other sources, especially to manage variants. This is a fundamental importance, and of course to make a traceability of all the changes. Now, this kind of data model sounds quite complex. So our concern was, okay, how do we get people to use it? We need to think about usability, and we tackle this by creating some user-friendly graphical user interface, because people are typically working by spreadsheets, as we said. So we know all the troubles, but these are very, very easy to use, so they're well accepted. We wanted to get rid of all files, but we wanted to retain that kind of simplicity. So what we did was to develop some spreadsheet-like interface. So we have developed some facilities for which, based on the data structure, the related GUI in a kind of a spreadsheet-like interface can be generated automatically to present the data for input in a very user-friendly way, with all the typical features like copy-paste, editing arrays, and so on. It's fundamental that this is automatically generated, because then you keep the flexibility of being able to adapt and create new engineering data containers for whatever application domain. Okay, the next is about the capability to reuse the data, to capitalize on this data. We need to make sure that once we invest in storing the data on such a system like cycle management platform, this can be easily accessed and reused because this is actually the base for value. You remember I mentioned commonization, I mentioned reuse, but also think about the possibility for data science, artificial intelligence. For this, we need high quality metadata, and this is the way to get it very quickly. So first, we secured the possibility to be able to compare at any level, starting from the specific data object up to the data container, up to the entire system structure for two systems, maybe coming from different projects or different project phases, to spot easily the differences. We went one step forward. Once we have data which is linked through this structure, basically anything in the database can be used as the object of a query or can be used as a criteria of a query. So we developed what we call the visual query builder, where graphically we can build complex queries where the search criteria can be data which is connected to the system we're looking for. For example, we may want to search for suspension which has a specific hardpoint characteristic or which is used in vehicles with a certain body mass. This is only possible when you have a data model which connects all these properties together. Finally, we mentioned a flexible way. We don't know what the future will bring like. So of course we need to have some capability to interact with any third-party toolchain. So in this case, we secure that all the data can be accessed not just by the native interface, that can be exported, can be queried in different ways, maybe by web services and so on. So we have the full flexibility of connecting this to other systems and data sources. Lastly, once we have the suitable and flexible enough data model in place, now we can start building maybe cross-functional processes with some confidence that this can be robust. I will give you two examples. The first one is about how we treat dynamic bushing data. For those who develop dynamic performances like handling, comfort, or noise and vibration, this is a fundamental component. So typically we have a characterization of these elements by either design data or test data. But what happens is that typically we use a mathematical representation in our simulation models. For this, we have in Toyota a parameter identification tool which can determine the value of these mathematical parameters from the design or the test data. We demonstrated the possibility to put in the loop this parameter identification process so that the engineer just needs to care about storing the design or the test data, and then the simulation model or the information needed for simulation models can be generated automatically. The second example is about the formal process to release and approve the data, which is fundamental to make sure that not only the data is up to date, but is guaranteed to have high quality. So you remember I mentioned before the milestone. So what happened is that at the milestone, there would be a model owner which would kick off a request for a modeling process. In this engineering data container, we can associate who is the data owner. And this data owner, we can get notified of a request to fill in the data. This guy can enter the data or just check that from the previous to this phase, basically his data has not changed, and can mark as checked for his manager to be able to be notified when the data input has been complete, and then can go through the typical review process. So once the engineering manager approves the data, then the data gets released, and we are sure about the data origin and quality. Okay, so far we didn't speak much about the simulation. So let's get back to the how to use this system structure as a foundation for SPDM. Now, we have a complete system specification, which is managing information about variants. It's traced across the development in different phases. So at certain point in time, we can ask for resolving a variant to get one specific system. In case of a car, it's one variant of a car for a specific phase. From this point, then, I mentioned before we wanted to use this data for simulation models, which may have a different structure, what I call here the simulation BOM. We were able to demonstrate the possibility to create simulation modeling rules which are able to place at the correct place in the simulation BOM the data coming from the system specification structure. This is an example of a multi-body model, a simple model. We can place the data for the flexible body, simple powertrain model, all the dynamic bushing, and so on, provided, of course, that we have the correct simulation model templates in place. Finally, by one click, we can get the model ready to run. Now, this is fundamental because what we are showing here is the full traceability of the data in the model from the system definition. So we're going from a system specification lifecycle to the simulation model lifecycle, which is not shown here. That's the part of the digital thread which follows. This is fully flexible. I'm showing here an example with SIMPAC, but basically if the system specification and the related engineering data containers have been designed correctly, basically this can handle any system complexity or simulation tool. Or even throughout the project, maybe at the beginning we would use a more simplified system representation, and later when more information is available, we can use a more detailed representation. So we think that with this, we managed the basis to handle through simulation complexity and even enabling the digital twin. Let me talk a bit about the scalability of this process. So what I showed now is the capability to handle system variants, so the actual system specification in the various variants throughout the life cycle. And this is basically what I here have in my rows in this table. And then by the solver rules, I can translate this into simulation models for various disciplines. Now, this is the basis for doing this with a full automation, which enabled to do a full coverage of the virtual validation, or just select what would be the worst case for physical testing. Because for us, generating one model or 100 model variants would be the same in terms of manpower. The example 2, how do we get from here to the digital twin? We can trace basically different system condition. So we can say, for example, that the system structure at the end of the development process would describe the system as designed for a specific variant. But maybe for that variant, we are building a prototype where something is built in consideration of some constraints. Maybe supplier is not the final prototype part, so we reuse something else. So with this kind of flexibility, we can manage what actually would be the content of the actual physical prototype. And we can update the system with data coming from the field, only as a revision of a previously developed system structure. Okay, so I think we explained somehow a vision for what to do with the connection of the digital thread to the SPDM world. There is still a lot of things to be done. First of all, we have to consider still how to build the rest of the simulation tool chain. Our vision is that in the future we would have one-click process, no more from a simulation model to a performance evaluation, but from an engineering data set. Because through the selection of the load case, basically in the background we could have the model generation with appropriate level of fidelity for that specific load case. And this data can be then traced back by the requirements which are associated with the system specification. If we are able to realize this process, basically there is no more data copy-paste, manual process, and so on. And it means that anyone who has access to this system lifecycle management platform would be able to leverage the power of simulation models to predict the holistic system performance. Once we can do this for 1 or 5 or 10 simulation, maybe we can do this for hundreds or thousands. And therefore, we can enable an easy way to do design space exploration, maybe assisted by machine learning algorithms. This way, we can really unlock the simulation power to handle uncertainty, maybe early in the design phase, or assessment of the worst case detection, or robustness considering the variability in a validation phase. And last but not least, still talking about digital thread, we need to consider how to integrate this with other existing processes. For example, we would like to be able to feed the data and the system structure from other sources when these exist. Think about all the data that you may already have in your existing PLM system handling detailed product structure engineering BOM. So for example, typical would be information about mass and inertia. This could be extracted automatically and then connected to the data of the specification at the system level. So in general, I think there is still a long way to go to realize the full digital thread with the benefit, but I think we have a so good path ahead. So in summary, I think it was quite a good experience with this proof of concept project. We believe that the enterprise deployment of simulation process and data management is a quite steep path. We moved firm steps in the right direction. We demonstrated the implementation of a system-centric engineering data model, including the feasibility of a flexible single source of truth for holistic thinking, for systems thinking, with all the related engineering data live that can be easily reused. We thought about making this easily accessible and reusable for either man-driven process or automated processes. And in particular, with processes automation, we demonstrated that we can actually unlock more efficient cross-functional collaboration. So with this, I would like to move to the conclusion, getting back on what Jay presented. Maybe Jay, you want to make some comments about the key takeaway points?
Yeah, so to cap the discussion here, so one of the key takeaways I would say is that when you design simulation models, right, and the interaction mechanics, be aware that the single source of truth changes over time. It is logically single, right? But it's physically distributed. So you need to plan ahead for the simulation workflow and model interaction to evolve and keep up with the system model. And you saw how one particular good use case of how Ernest does it. And again, and this is one of the questions which I'm going to pop you, Ernesto, during the QA, is that what was the role of suppliers and your vendors, how you distributed the system model? That's a question I have for you later. The second takeaway is that the SPDM or SLM architectures, they have to support distributed and collaborative simulation. So when you start collaboration, the kind of parameter, the kind of model interactions that you assume, keeping it in-house, that changes drastically. So distribution and collaboration is not an easy topic. So that the simulation world hasn't scaled up to that yet. So the current PLM-based architectures cannot keep up with the complexity required for multidisciplinary, multi-physics simulation data management. Your turn, Ernest.
Hi, thank you. Okay, from my side, indeed, we tried to touch upon some of these ingredients. Our key point is that before we start talking about simulation process and data management from a system thinking perspective, we need to consider a flexible and system-centric data model. Without this, we would really struggle to build upon some efficient process. We think that historically it's not been very much developed. It's something quite new. So in general, if you want to consider a system performance simulation domain, you may need to consider some custom development. Difficult to imagine some out-of-the-box solution which is truly tool independent. And then I hope I could show you some hint how there is a better potential for utilization of simulation when this is actually connected across domains to engineering data, and can realize process automation with surrounding processes by digital thread and node-related automation. Okay, so I think this is the conclusion today. There's one more point I would like to touch. It's quite complex matter. It's quite tough to move along. So I would like to use this opportunity from NAFEMS with such a good audience to have a call for action to accelerate on this SPDM development. So we said, okay, this is not just one domain and one tool chain. In spite today I presented what is closer to my professional experience. But in general, what I've seen is that always we have new technology. We don't know if tomorrow we'll be using the same simulation tools and tool chains as today. So we need this kind of flexibility. Therefore, we need a truly tool-independent process integration. I hope I could explain through the example of our POC what I mean having an open and flexible data model. We didn't touch much on open APIs and standard to connect the different processes, but I think this is really also key to be developed. Considering also that the customization we're talking about should be managed in a way that doesn't create what is called technical debt. So the problem of being locked into something that cannot be easily modified. So with this in mind, I would like to call for teaming up at pre-competitive level between like-minded people across industries to accelerate the needed technical development, like discussing together what kind of requirements need to be implemented, what are the different technology assessments which have been already ongoing, and working with vendors to jointly develop demonstrators like the one that I presented. So I would like to conclude with an invite to get in touch if you are interested in such a collaboration, because yeah, I think maybe we can have a lot of potential from learning from each other and working together. Okay, this time really I think I've finished. So thank you very much for the attention, and Andrew, probably from this point we can open the Q&A.
Thanks, Ernesto. And thank you to Jay and to Malcolm as well for these excellent presentations. So we'll move into the Q&A portion here. Now remember with your Q&A questions to use the Q&A feature box to send those in. And we've got quite a few sent in already, and I'll take the first one. I had asked some questions, a few people were wondering about copies of the slides and the recording. So we will work with the presenters to try to get the content approved. If it is approved, we will post the recording and the slides on the event webpage for the community to view. Okay, all right, so we'll start with the first question here. So I believe this one's for Ernesto. I'm with you on the idea and benefits of integration of data and bill of material, but wondering why you've written your own PLM system. What's the business case for that?
Okay, so the business case. As I said, we wanted to develop something which we could easily connect to simulation models. So one struggling point we have seen in the past is on the capability to handle live data. So pretty much any PLM system can handle things like strings, scalar data types, and so on. But when it comes to a bit more complex data types like arrays, maps, and so on, this is a little bit more difficult to do. So that's what was driving the need for having a bit more custom developed data model to have an easier connection through modeling rules to simulation models. I hope I understood and answered the question. Otherwise, please get in touch. We can discuss further offline.
Okay, thanks, Ernesto. Next question is for Jay. Jay, can you explain the difference between hierarchical and model abstractions?
Yeah, the hierarchical abstractions come from the product structure. They have the basis there, and then you kind of, when you get from the standard product structures, when you get into the simulation side, you rearrange the structures to depending on what is that you're simulating. So there is a mismatch there. So again, for different types of simulations, you use different kinds of structures. So there's a misalignment in how the hierarchy is managed. So that the coordination of that has to be captured by the simulation lifecycle manager. When I say model abstractions, that is, we are talking about models, from a 1D perspective, 2D, 3D, right? So so the various fidelities of the model that we use. So the combination of these is a matrix, and that needs to be configure managed and tied to the systems model, and that needs to happen at specific points. And one of the key things about this, you don't want, when you do this, your interface interaction gets very complex. So there are equivalents in the software system world called, there's a newer concept recent where it is gaining traction in the software architecture world called the domain-driven design. One of the key ideas in domain-driven design in software architecture is that you have this thing called the bounded context. You manage the complexity of the domain within its domain. Don't let it leak through the interfaces. So when you have these abstractions, make sure it is either contained within the domain, but if it has to reach out outside the domain, make sure you manage the interfaces, the change on the interfaces that's coming. So in the context of this question, there are both the model hierarchies and the model abstractions both have to be managed at the interface when the two domain models interact.
Okay, thank you, Jay. And next question for Ernesto. Is Toyota developing this SPDM tool internally?
In this case, yes. So we started from a base of a commercial open PLM system like ours. We used, where possible, the basic infrastructure capability and the basic data model, and on top of this, we developed what I presented today. So there's no one fits all. So I'm not aware of anything which fulfills exactly the scenario that I described here. So in this case, indeed, we wanted to test the feasibility of exactly this kind of workflow and capability. So this was developed from the data model.
Okay, thank you. And the next question, how much time was needed for the POC project?
I would like to ask the person who asked this question what would be his estimate. Actually, it was not that long. We had a pretty tough discussion at the beginning on the requirements. I have to say we changed our mind in some cases, and our partners also changed their mind. Finally, we got a pretty good alignment before starting. So this was, I think, a fundamental point. We needed to understand each other and learn from each other what we wanted to create or what the counterpart could offer. Once that kind of agreement was reached, it was quite fast. I think it was around 3 months to develop this demonstrator.
Okay, thank you. And
I will not mention the amount of coffee that that was consumed during the development, but yeah, it was relatively fast, I think.
Most important element sometimes. And next question, how easy is it to find engineers with sufficient systems, simulation, and data management experience to build and use such a system?
Okay, build and use. I think it's a completely different story. So as I said, let me start from the easy one, use. We developed usability exactly because this, to be successful in the organization, it needs to flow as much as possible in the daily work of people who are nothing to do with big management. They have to do their work, they have to design specification, they have to achieve milestones, be on time. So usability was quite an important part of this demonstrator, because indeed, if we have a perfect system, but basically people will not be willing to use it, then it will not be a success. So to use the system, in my understanding, will not be so challenging because we thought about the usability. Developing it, it's a different story. Indeed, you need someone in the organization who has the clear vision of why he wants to achieve this kind of data model. You need a drive on the organization side for someone on the development side and someone on the user side who jointly can work to define the specification. And then you need capable people to implement it. So build, no, definitely not easy. Not easy at all.
Okay, thank you. And next question, can you please share some background about the IT architecture used for the Toyota POC application?
Okay, so for this POC, it was quite an easy one because it was an on-premise server implementation. But when we were developing the POC, we were investigating also the feasibility for having a scaled implementation. So for the POC, pretty easy, but you need to consider carefully if the POC is successful, okay, what do you do next? How to make sure that you build something that it would be possible to access from all the different development centers, that you will be able to open to suppliers in future and so on. So I'm not an IT expert, so I cannot probably answer on what a working implementation would look like. But for a demonstrator like this, I think just a on-site implementation is enough.
Okay, great, thanks. And next question, do all tools you're using have the appropriate APIs to allow automatic generation of models as required by your vision?
That's a good question. That's a good question. So let me say that one of the most important API is called TXT, text files. So you can't imagine how much automation you can do through some text files and some Python scripting. No, not everything has a very good API, but indeed we try to build where possible process automation starting from developing really simple text files.
Okay, thank you. And how important is it, in your point of view, to consider different engineering roles for the users of SPDM?
Fundamental, because okay, today we spoke mainly about the tools, but finally we want to realize a process. So okay, I didn't touch on the roles very much in this presentation, but we started from an actual workflow where we depicted different roles of people who have different stakes in the system development. And this finally affects the data model itself, because imagine, for example, that you need to make sure that there is somebody who is the owner of a system structure, somebody who is the owner of the data populating the leaves of the system structure. So indeed, do not underestimate the process you want to realize, because that may affect the engineering choices you have to make about the implementation of the data model.
Okay, thank you. And next question, in software building, one would intentionally create modules with intentionally limited interaction. Doesn't this imply a need to build silos rather than simply dismiss them as a legacy approach?
This is for me or for Jay?
This one is open.
So, I mean, what do we mean by modules here? I mean, modules could mean multiple things in software, so it needs some clarity.
So if the person that sent that question, if they could just follow up with a separate question, we'll try to get to it towards the end here. And next question.
Hey, Andrew.
Yes, go ahead.
Let me perhaps jump in on this. This is Malcolm. I see that Peter has asked that question. It's not a matter of dismissing silos as a legacy approach. Silos exist in any and every organization that I've worked with. They are a reality that, whether you wish to or not, exists. What's needed, though, is the ability to bridge those silos appropriately, to, as Ernesto said, allow teams of engineers that could be geographically distributed and certainly within different silos to be able to collaborate, work together on creating central data structures that can then be reused across the organization. So it's not a matter of dismissing silos as a legacy approach, but embracing them as reality, but then making sure that your backbone and your ability to communicate and your ability to create data is not hampered by the existence of those silos. Andrew?
Okay, thanks, Malcolm. All right, and next question. Which standards for simulation do you consider most important to realize your goals? Which ones are needed in the future? So this one, I believe, is open as well.
So I can take some piece of this. So there are a few standards that are developing. One of the most important probably is you need to look at, especially from a distributed simulation perspective, is this standard called MOSEC. It's now on the way to become a STEP standard called STEP AP243. So please have a look at it, mossec.org. So that's one thing. And also one of the key things about that standard is that it's based on PLCS, which takes a true product lifecycle view of standards, so of data. So it's based on a strong foundation of the true lifecycle. So it meets all the way to support. So you can take data from simulation data from not only just design models, from for example, from as-built digital twins as well, and there's possibility to tie it to that way, and there's underlying structure is there. I mean, there's notion of product as an individual, so you can say tie simulation data to that and bring it in. So it's not just a pure design-centric standard like STEP AP242, which is kind of focusing only on design. So that's one thing that I want to look at, but also from a RFLP perspective, from the requirement side, of course, there is STEP, that's the elephant in the room, but from the requirement side and configuration management side, there's another good thing to look at is OSLC. That is, it's based on the RESTful web services, and also it's based on RDF, the subject object triples. So subject predicate object triples, and so you have a way of exploring traceability that is required for your system model, and even all the way to simulation models and your tests and results. And you can make those queries, traceable queries, using another standard called Sparkle. There is an effort in the standard space right now to make many of these data models graph-based, so that you can start querying them, and they're at various stages of maturity. And some of you who kind of focus on this also kind of ties into the API question that was asked a moment ago. So this also ties to that, is that in the SysML2 version 2 specification, there's a specific working group for APIs. So that is another thing to look at. That is from ONG. So that's another standard that you need to look at, from what does API mean in the context of system model. And as you go forward, that is one of the expectations that you will, I would say probably any tool that claims to be a SLM or SPDM in 5 years from now, a compliance to these standards should be commonplace. Otherwise, I don't think it can carry that tag. So I mean, because this thing, the simulation activity is going to be very distributed, and right now it can't be in one box. It has to be distributed. So that can happen only with standards.
Okay, thanks, Jay. Next question is for Ernesto. What level of customization is required for the data model? Are there specific requirements on types of customization?
Whoa, okay. I guess this depends on your organization and your process. So I mentioned some of them during the presentation. So on our side, we wanted to be able to manage variants, for example. We wanted to have a flexible system definition so that we could use from early stage, we could use for multiple domains. We wanted to have the capability to tag data objects to specific owners. We wanted to have their traceability. We wanted to have the additional tags like, I don't know, data being checked or data be approved, and this linked to complex data types. So this was the result of the current simulation process we tied as a data model 2 with a view on what's coming in the near future. So I guess this really depends on what your industry is doing, what kind of product you are developing, and what kind of organization needs to be relying on such a data model. I really recommend that indeed you start from a process flow, and from that one you start deriving the requirements for the data model customization.
Okay, thanks, Ernesto. Next question, do you have any practical advice on how to increase the flexibility of a data model?
Practical advice. Yeah, indeed, try to separate as much as possible the data model from its user interface. I think try not to get locked into a data model for a particular application. Yeah, that's what I would really advise.
Yeah, so I would like to add a little bit on that. So when we say data model, right? So we have been using the traditional relational data models and also slap the XML over it, and we have XML schemas. So those are all rigid closed data models. Once you put them, unless you have an object-oriented practice, you can't really make the data models extensible. So some tools allow for an extensible data model. For example, most PLM tools, what the only extensibility that they allow is to allow you to create types, right? And everything that you have is based on whatever you could do with the type. But for a more fundamental change in terms of conceptual, if you want to bring in new concepts, and so some of the things in those areas you need to look at the concepts of ontologies, which look at open world assumptions, right? So what is true could be false tomorrow, or what is false today could be true tomorrow, right? Depending on the arrival of this new fact. So that would, when you get onto such complexities, you kind of look at what is it from a relationship perspective between the data. So it allows you to traceability. That's one of the key topics of digital thread is traceability, right? So one of the data models that we look at from the SPDM perspective is what is that data model that allows speed traceability? So with new facts coming into the mix. So that is an effort that's going on in many standards organizations right now, how to make this RDF based and allow queries across multiple domains.
Just to add a bit to that, we've lived in a world that's been dominated by particular point tools that have offered us particular capabilities in certain areas, all the way through the product lifecycle. That's often resulted in data structures and data models that are tool specific. That has been the biggest issue when trying to figure out how to handle your own data appropriately, because they tend to end up in these particular data models that are tool specific. My key advice here in terms of flexibility of your data models is that each company ought to determine first what data they wish to manage. And Ernesto alluded to this earlier. Develop the data models specific to your particular data and ways of representing the data and processes, and then communicate the information to your tools as appropriate. In other words, maintain your digital thread information to be completely tool independent. Andrew?
Okay, thanks everyone. So we just have time for just one more question. So is this for Ernesto? Is Toyota looking at formal systems engineering, system architecture, system analysis before getting into model-based design of 1D systems?
Of course it is. Of course it is. At the moment, I cannot disclose much, but yes, I mentioned before upcoming different products or something that looks maybe different from the typical vehicle we design. That requires probably a different way of looking at the concept of platform development and different systems interaction. So this kind of complexity indeed requires a more thorough approach to the system thinking. Yes, this is definitely under investigation.
Okay, thanks, Ernesto. All right, and just again, I know a few more questions came in about recording and slides. So again, we'll work with the presenters to try to get the content approved. If it is approved, we will post it on the event web page, the recording and the slides, probably in a couple weeks or so. So you can make sure to check back then on the web page. And if you have, we weren't able to get to everybody's question today, so I'll just leave this slide up here for a moment where you can take a look at the emails there if you'd like to follow up and certainly do so if you have more questions. So again, thank you to Malcolm, Jay, and Ernesto for these excellent presentations today. And also thank you to everybody that attended today. We appreciate your time and have a great day.